Okay, good morning. Okay, so let's start the class. So today we will talk about a new topic, and then we will include this in the final exam. Okay, so we will talk about something called the planar graph. So this is the definition. So a planar graph is an undirected graph such that we can draw it on a plane without any edges crossing. So what does it mean? So for instance, this is a graph with 4 vertices and 4 edges, and then it can be drawn on the plane, and then there is no edge crossing each other. So in that case, this is a planar graph. Is that okay? And how about this one? Let's try this one. So this is a K4. So this is a complete graph with 4 vertices. So is it planar? Well, in this drawing, we do not see that it is planar directly because there are 2 edges here crossing each other. But it doesn't mean that it is not planar. So a graph is planar if there is a way to draw the graph without any edge crossing. So if you label this graph as these vertices as A, B, C, D, we can redraw this graph in a different way. So we have A, we have B, we have C, we have D, and then we have this one, this one, this one, this one, and this one. And if we can draw the edge BD without any edge crossing, then this can show this is a planar graph. And in fact, we can do so. Okay, so it is not necessary that the edge is drawn by the shortest straight line joining the 2 vertices. We can join them like this. Is that okay? So this still represents an edge joining the 2 vertices B and D. Okay, so in that case, K4 can be drawn without any edge crossing each other. So K4 is also a graph that is planar. Is that okay? Okay, and then let's do some more example. So Q3. So Q3 is what? Q3 is a 3-dimensional cube. So it looks like this. There are 8 vertices here. So because it looks like a cube. So these are the 8 vertices, and then this one joins to this one joins to this one. Okay. Is that okay? Yeah, maybe I'm not that clear about this one. So let me change this edge a little bit. Is that okay? So this is a 3-dimensional cube. So there are 8 vertices. So the first 4, they form a square. The next 4, the other 4, they form a square. And then we have an edge joining the corresponding vertices in the 2 squares. Is that okay? So this is a 3-dimensional cube. And in fact, this is also a planar graph. So let me call this A, B, C, D. And let's call the other 1, 2, 3, and 4. Okay. So we can change the graph like this. So we have A, B, C, D, C, D, drawn in the center. So this is one way. And then we have 1, 2, 3, 4. We have 1, 2, 3, 4 as a large square outside. And then we have 1 joining to A, 2 joining to B, 4 joining to D, and 3 joining to C. Is that okay? So if you look at it, then this is Q3, and this is also Q3. And then in this graph, in this drawing actually, we can see that there are no edge crossing each other. So Q3 is also a planar graph. Okay? And in fact, whenever we have a planar graph, and then we have a drawing that shows that it is a planar graph without any edge crossing each other, then this is called a planar embedding of the graph. So embedding means you're lying on the floor. So you embed the graph, you put the graph onto the plane, and such that it shows that there is no edge crossing each other. Okay? So there are some more examples. So for instance, we have studied bipartite graph. We have also studied complete bipartite graph. So let's consider K1n. So what is K1n? K1n means that I have one vertex on one side, and then I have n vertex on the other side. So this is a K14 that I'm going to draw, so that we join an edge between every pair of vertices, one on the left and one on the right. Is that okay? So this is a K14. So it is very easy to see that K1n must be planar. Yeah, you draw it like this, and then it is a planar graph. Okay? And in fact, K2n is also planar. So what is K2n? K2n is like this. So you have 1, 2, 3, 4, 5. Let's say I'm trying to draw a K25. So we have 2 vertices on this side, 5 on this side, and then we join each pair. Okay? So this is a complete bipartite graph. So it is complete because it has 2 vertices on one side, 5 vertices on the other side, and we have every edge possible that we have drawn. And then it doesn't look like it is it doesn't look like it is planar, right? But it is in fact planar. So how do you see? So you pick up this vertex, you move it to this side. Is that okay? So this is like you have a K1n, you have another K1n, one vertex on this side, one vertex on this side, joining to each other. Is that okay? Okay. Now, but somehow, some graphs are not planar. We will show that some graphs are not planar. So for instance, K5 is not planar. So K5 is like this. So K5 is, you have 5 vertices, you have edges joining every pair of them. So I need to join these 2, I need to join these 2. Is that okay? I still need to join these 2. Well, I can join these 2 by having an edge like this. Am I correct? I still need to join these 2. Well, I still can join an edge like this. But somehow, using what I've drawn so far, there is no way that I can join these 2 without crossing any existing edge. Okay, so, but that doesn't mean that, okay, so that doesn't mean that I'm showing K5 is not planar by using the arguments so far. Maybe I am just too not clever. I do not find a correct embedding of this K5 on the plane. So we somehow need to show that for any person in the whole universe, this person cannot find a planar embedding of this graph. So we will somehow show that, okay, by arguments that this must be not planar, no matter who is going to draw. There is no way to make it planar, looks like a planar graph. And there is another one, K33. K33 is also not planar. So we will show this today. So K33 is like you have 3 vertices on one side, 3 vertices on the other, and then you join them all. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. And no matter how you do this, then there is no way to make it look like a planar. Okay? So how do we show these results? We are going to introduce an Euler formula. Okay. So we have something called the Euler planar formula. Euler is very clever. He has observed that for any planar graph, there must be something that it has to obey. So we have something called the Euler planar formula. So I will talk about this soon. But let me define some concept. Okay. So let's have a, let's draw a planar graph, for instance. Okay. Okay, so this is a planar graph. Is that okay? Now, we use, so for simplicity, let us use V to denote the number of vertices. Let us use E to denote the number of edges. And now we can talk about regions. Okay. So these three vertices, they have edges joining to each other. They form a cycle, right? And then this cycle does not contain any edge inside. So there is a region. It may contain things inside. So there's a region 1. Is that okay? There's another region here 2. So if you imagine, if I drop an ink, a red ink inside this part, and then this ink can go wherever it wants, then it will color all this part into the same color. Is that okay? So this is another region. Is that okay? And then this is another region. So this is region 3. And then there's actually one region, let's call it region 4. That is the whole big thing outside. So in this case, there are 4 regions. Is that okay? Let me, so as another example, so how about this one? So how many, okay, so how many regions are there? 2. There are 2 regions. So there's 1 here, and there's an outer space, there's a 2 here. Is that okay? Okay. So for some reason, although region starts with R, I'm going to use F to represent the number of regions. Okay. Because regions, okay. Because actually, at the beginning, F stands for faces, number of faces. So you will see why we call it faces. Okay, so Euler planar formula says, for any planar graph, in any of its planar embedding, we must have V plus F is equal to E plus 2. So this is the so-called Euler planar formula. Okay. So if you look at it, so the number of vertices here is 1, 2, 3, 4, 5, 6. So in our case, V is equal to 6. And then F, number of faces, number of regions, turns out to be is equal to 4. Is that okay? And how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 edges plus 2. Is that okay? Now this is so amazing. Okay, so this is in any planar embedding. So somehow, okay, so let's take a look at this K4. So this is a K4, okay. But this is not a planar embedding because it doesn't look like planar. There are edges crossing, so we may change it. So there could be different ways of drawing this and looking at it like a planar graph. So one way is this one. Is that okay? We can have another way. This is also possible. We may actually have another way. Yeah. Okay, this is another way. Is that okay? This is also a planar embedding of the same graph. Is that okay? But still, for all of the cases, so in all of the cases, the number of vertices and the number of edges must be the same because it represents the same graph, right? But you will see that in any of this drawing, the number of regions are the same. So there are 1, 2, 3, 4. Is that okay? There are 1, 2, 3, 4. There is, okay, there is what? 1, 2. Yeah, so this is, so let's color it. So this looks like a region, right? Is that okay? So you can see that there is 1, there is 2, there is the outer space 3. Is that okay? And there is this kind of thing, 4. So there are still 4 regions. Is that okay? So in any embedding of a planar graph, it has to obey this rule. And okay, so this is my way to remember this. So because Euler is very, very smart, okay, and famous. Okay, so this is very famous Euler. And then how about this too? Yeah. So this is very famous Euler. Yeah. Okay. So this is how I remember this. So why do we call it phases? So perhaps I can tell you why. Okay. Look at this one. What does it look like? Does it look like a okay. So remember, we have some cube called tetrahedron. So it looks like a pyramid. It's a cube, right? Yeah, imagine this is a 3D shape. Okay, it's not a graph, it is a 3D shape. So this is a cube. No, a cube, this is a 3D shape. We call it a tetrahedron. Now, if you move our eyes on the top, then what will we see? We will see what? We will see this is this vertex. And then we are going to see these 3 vertices at the bottom, right? And then we will see that they are joining to each other like this. Is that okay? Is that okay? So actually, so this is why we have a face here, a face here, and a face here. So these are the 3 faces that we see. And how about the bottom? The bottom we do not see. So we use the outer space to represent it. So in fact, why we call it F, it is because we look at some objects of a planar graph. So if we imagine this planar graph as a certain kind of 3D object, and somehow it becomes faces of the object. So similarly, so we have a cube. So this is a cube, okay. So we have drawn a cube already. So this is a cube. Is that okay? So somehow, if you, I don't know, if you enlarge these 4 of them a little bit and look at it from this side, then we will see something like this. This is what we have drawn. So that this represents, maybe this represents this surface. Is that okay? And then we have 1, 2, 3, 4 represents the top, the right, yeah, we look at it, the bottom and the left side. And if we are seeing on this side, we don't see the back. So we're using the outer space here to represent the back. Is that okay? So that's why, yeah, so that's why we have this one. And later we will actually give a connection, okay, of Euler planar formula with this kind of regular objects that we can see in real life. Okay, we haven't shown why this is true, and it is actually easy to show. We can show this formula to be correct by induction. So how do we show? So you just give me any graph G, and then give me its embedding in the plane. So we have start with this embedding of G already. So we start with a planar graph G, and then we got its embedding. And then we are going to look at, so this is not just any planar graph. I need it to be connected. Okay, so connected is needed. Okay. So the graph needs to be connected. Okay. So we have a graph G. We start with the embedding of G, and then we start realizing this embedding by adding the edges one by one, or adding the vertices one by one. So every time we will make the graph connected. Okay. So let's give an example. So for instance, this is a graph that we have. Okay, and this is a planar embedding. So what we are going to do, we are going to start with a single vertex because we want to make everything connected in the process. So we start with any single vertex, let's say A. Okay, so we get a single vertex A, and then what? And then we add an edge. So each time we add an edge. So we have A, so we can add an edge. So which edge we want to add, no matter which edge, is always okay. Let's add B. Okay, so let's add B. So we add this edge. So this is still now connected. Okay. And then we further add an edge. Maybe we add the edge, what? We add the edge C. Is that okay? AC. Because there is an edge AC. And then after that, we add one more edge. So we have A, B, C. Maybe we are closing this one. We add the edge BC. Is that okay? So every time, what we are going to do is we add an edge. We start with a single vertex at the beginning, and then we add an edge. So that at any step, the graph is connected. Is that okay? Okay. Now, let's look at the change in the V value, E value. So we want to try to look at the change. Okay, so we use delta. The change in the V value, the change in the E value, and the change in the F value when we are doing this adding process. Okay. So we start with one vertex at the beginning, so we ignore it. But now, if you look at it, what will happen? So in this case, we are adding one vertex, and at the same time, we're adding one edge. Is it okay? So we have delta V increases by 1, and delta what? E increases. And each time it is increases by 1. Increases 1, increases 1. Is that okay? Is that okay? And how about this one? For this one, we are also, from the change from this one to this one is we are adding a new vertex C and then adding a new edge at the same time. So this is similar to this one. So the number of vertices will increases by 1, and then the number of edges will increases by 1. Okay, is that okay? Now, the change from this one to this one is a little bit different. So we don't add new vertex. We are still using the same set of vertices A, B, C. Okay, but we are what is changed? What is changed? So we add a new edge here. Am I correct? And then when we are not adding a vertex, we add an edge. Then that means what? We are closing a region. This means that because the reason these two are already connected, they are connected. And then we join them together, so we are closing a region. When we close a region, we increase the region by 1. So in that case, we have the number of edges increases by 1, and then the number of faces also increases by 1. Is that okay? Okay, and actually, there are just these two kind of situations. Either we are adding a new vertex with a new edge at the same time, or we are not adding new vertex. So in that case, we are adding an edge, but joining a region, closing a region. So either we will have V and E both increase by 1, or we will have E and F both increase by 1. Is that okay? Okay, now let's look at this case, this graph. This graph obeys the formula V plus F is equal to E plus 2. This obeys this formula because of what? Because number of vertex is 1, the number of face is 1, the number of edge is 0. So 1 plus 1 is equal to 0 plus 2. If you're okay with this, could you please raise your hand? Okay, good. Now, and this one follows V plus F is equal to E plus 2. How about the next step? This next step will increase V, E both by 1. So we increase V and E both by 1. So the equality still hold. Is that okay? And then the next step also V and E increase both by 1. So the equality still hold. And then the next step over there, we are increasing E and F both by 1. So this equality still hold. So no matter what we do next, we either increase this one and this one at the same time, or we increase this one and this one at the same time. So this formula will always hold until the end, until we have drawn all the edges. So that's why the Euler planar formula is correct.